This is the problem I was assigned. Please pause to read. So the important things that this problem tells us is that heat energy is released from 2 to 3. And you can also tell from the diagram that pressure increases, but the volume stays the same. That means that this process is isochoric. And the same thing happens over here, where we're going from 4 to 1, the temperature drops, and similarly the volume stays the same, which means that this process is also isochoric. And we already studied before, and we know that during an isochoric process there is no work that is done. And you can also tell because the area under these curves is 0, so the work is going to be 0. So the processes during which no work are done are from 2 to 3 and from 4 to 1. So the processes during which there is work that is being done are going to be from 1 to 2 and from 3 to 4. And these are adiabatic processes in which no heat is gained or lost. So you can tell from the diagram that there is both going from 1 to 2, there is both a change in volume and in pressure, but the temperature stays the same, or basically no heat is either gained or released. And same from 3 to 4, there is change in pressure and temperature, but there is no heat gained or lost. So how can we find what the work done per cycle is? Well, we know that the work done in an adiabatic process is equal to the change in energy, which is equal to the negative number of moles times the specific heat at constant volume times the change in temperature. So knowing that, we can find what the work done is for going from 1 to 2 and going from 3 to 4, and we're going to get these two equations. Then we can add these two equations to find the total work, and then in order to simplify the equation, we can take that the specific heat ratio is equal to the specific heat at constant pressure divided by the specific heat at constant volume, and the specific heat at constant pressure is equal to the specific heat at constant volume plus R. And so we can combine these two equations and rearrange it, and we're going to get that the specific heat at constant volume is equal to R divided by the specific heat ratio minus 1. So if we were to plug this in for the specific heat at constant volume, we would get that the total work done is equal to the number of moles times R divided by the specific heat ratio minus 1 times T4 minus T3 plus T2 minus T1, which is the same thing as this. And then our professor wanted us to answer how the Otto cycle differs from the Carnot cycle. And first of all, the Carnot cycle, as you can tell, it has 2 isothermal processes and 2 adiabatic processes. And because of the isothermal processes, it is nearly reversible, whereas the Otto cycle has 2 isochoric and 2 adiabatic processes. Therefore, it's not reversible because of the isochoric processes. And so in the Otto cycle, when heat is added, the volume stays constant. And this is, as I stated previously, this is what makes it an isochoric process. The volume stays constant, whereas in the Carnot cycle, that's not the case.